Hello, good morning. I am Dr. Kamanashis Goswami, Assistant Professor, Department of Electronics. Now, in this session, I am going to describe the working principle of a monostable multivibrator using op-amp. This monostable multivibrator can also be designed using discrete components or using 555 timer. But in this session, I am going to describe how we can design a monostable multivibrator using op-amp. So the circuit diagram of this monostable multivibrator is shown in this figure, in this slide. Okay. Now we can see from the figure that the positive input terminal, that is actually called the non-inverting input terminal, is connected with output through a resistance R2. Okay. So we can say it is having positive feedback. Now one combination of a capacitor C and D1 is connected to inverting input terminal, this point inverting terminal, which is also popularly called negative input terminal, and it is connected to output through a resistance R. Okay. Now this R2 and R1 is a voltage divider circuit. Okay. So if the voltage is V naught, so output, sorry, the voltage of this point, middle point, that is the midpoint of R2 and R1, is, we can say, R1 by R1 plus R2, which can be referred as feedback fraction, that is beta. So this point is connected to positive input terminal. See here, positive input terminal. So we can also say this positive input terminal is clamped at this voltage, that is known as beta V naught. Okay. Acha, which is, what is beta? Beta is called feedback fraction. Acha. Okay. Now before starting, let us recapitulate the differences of these three multivibrators. Now these three graphs shows the waveform generated by three multivibrators, that is astable multivibrator, bistable multivibrator and monostable multivibrator. See, in the upper one, it is actually the waveform generated by a astable multivibrator. Now the thing is, in case of astable multivibrator, see, it is the output or the multivibrator or waveform, it is having two states, 1 and 0. Now from switching from 1 to 0 or 0 to 1, in case of astable multivibrator, it doesn't require any external triggering pulse. See in this picture, if we consider it is a multivibrator and the output can be obtained from this point, so there may or may not be a extra triggering circuit. Okay. For astable multivibrator, as it doesn't require any external triggering, so we don't need any external triggering circuit. Okay. It is automatically switches from 1 to 0 and 0 to 1 and so on. That's why it is said it is astable multivibrator. Okay, we can say neither of the states are stable. Okay. The middle one is the waveform generated by a bistable multivibrator. Okay. In this case, both the states 1 and 0, both states are stable. Now what does it mean, stable state? That means if we don't apply any external trigger, the 1 will be 1 forever and 0 will be 0 forever. There will be no state change. Okay. So to change the state either from 1 to 0 or 0 to 1, we need a external triggering pulse. Okay. Now the last one, that is the monostable multivibrator. Mono means one. So either of the states, either 0 or 1 will be stable. Okay. And the other one will be quasi-stable state. So in this diagram, in this figure, actually we have considered the one state is stable. Okay. And the 0 state, it is quasi-stable state. Okay. So as we are saying this one state is stable, that means to switch from 1 to 0, it needs a extra triggering pulse. Okay. But to switch from 0 to 1, it doesn't require any external triggering pulse. That means automatically it will switch from 0 to 1 after a certain time. Okay. This certain time is actually the pulse width of the monostable multivibrator. Okay, now let us see. Okay, the working principle. Let us try to understand the working principle of this monostable multivibrator. So in this diagram, under this configuration, actually, our stable state is 1. Okay, this, let us say this is 1. So 1 is our stable state. Okay, it is 1. Now it will be 1. It will be means the output of the multivibrator will be 1 if we don't apply any triggering pulse. This is the point, this V in, where we can apply the triggering pulse. Okay, this C4 and R4, obviously the important point is, in this, under this, according to this configuration, the triggering pulse will be a negative going triggering pulse. Okay, see here, it is a negative going triggering pulse. We will describe why it is negative going triggering pulse. So according to this diagram, our stable state is 1. I have already said. Okay, so if it is 1, why it is called 1? It is a digital term of digital electronics. See, previously we have discussed that it is having a positive feedback. So if a op-amp is having positive feedback, it will work in saturation region only. See this diagram, this graph. Okay, this this is the transfer characteristics of a op-amp. Okay, so this is the saturation level. These two, upper one is called positive saturation level, negative, lower one is called negative saturation level, and this one is the linear level. Okay, linear region. Okay, so as it is positive feedback, it is having positive feedback, so it will work under only this positive or this negative saturation region. There will be no linear region. Okay, so this is actually practical transfer characteristics of practical op-amp. So in case of ideal, it will be, there will be no linear region. Okay, so it will be only positive saturation region plus V set, and this is negative saturation region, that is called minus V set. Okay, now the question is, when it will be positive sorry, when it will be plus V set and when it will be minus V set. It depends upon the difference of voltage in these 2 points. These 2 points means the input points. Okay, this is called VID. VID, what is VID? That is called input difference voltage. See here, VID. So VID is nothing but the voltage difference between these 2 points. Okay, that is VA minus VB. What is VA? VA is the voltage of this point, that is the non-inverting terminal, and VB is the voltage of this inverting input terminal. So VID is nothing but the difference of these two voltages. Okay, this VID, and depending upon the value of VID, either the output of the circuit will be either plus V set or minus V set. So it will be plus V set if the value of VID is positive. See, when the value of VID is positive, the output will be plus V set. Okay, and if the value of this VID is negative, the output will be minus V set. Okay, that means one thing is clear, that we are going to get only positive V set or negative V set. Okay, other than these two voltages, we are not going to get any other output voltage. Now this plus V set is actually nearly equal to plus VCC. Okay, we know in case of a op-amp we need two biasing voltage, one plus VCC, another one is minus VCC. So this plus V set is almost equal to plus VCC, and minus V set is almost equal to minus VCC, which is typically ranges from 12 volt to 15 volts in our laboratories. Okay, now there is another diode connected with this non-inverting input terminal in this manner. Okay, see, so this diode allows only negative pulses. Okay, if there is any positive pulse, it will be reverse bias, so it won't allow any positive voltages to come through this portion. Okay, and this C4 combination of C4 and R4, that is working as a differentiator, which reduces the pulse width of the pulse. Okay, that means it converts the pulse into spikes. See here, it converts the pulses to a spike. Okay, fine. Now let us see how it is working. One more thing, as the output voltage could be either plus Vset or minus Vset, we have already discussed the voltage of this point Va is beta into V naught. Okay, Va will be equal to beta into V naught. Now, as the voltage V naught could be having two values, plus Vset or minus Vset, so accordingly, this value will also change. Okay, so either this beta Vset could be either plus Vset or minus Vset. Okay, this is the important thing. Now, when it will be plus Vset, when the output will be Vset, beta into Vset, output will be Vset, and when the output will be minus Vset, the value of beta V naught will be minus beta into Vset. Okay, and obviously the value of this voltage beta V naught will be less than V naught because the value of beta is less than 1, obviously. Okay, now see, let us say the output is plus beta Vset, that is the stable state according to this configuration. Okay, so output is plus Vset, that is a positive voltage. So if it is a positive voltage, this positive voltage makes this diode forward biased. Okay, so there will be one current flowing through this path. Okay, this path, and it after this point it will try to divide into two portions. Okay, one current will try to flow from C, another one is from D, but as the diode is forward biased, okay, ideally we can consider it is forward bias means it is offering zero voltage, that is it is a short circuit, so current will follow this easy path. Okay, so this current will flow from V naught to ground through this D1. Okay, so this capacitor will remain uncharged. Okay, another thing is what will be the voltage of VA under this configuration? So VA will be plus beta into V naught. Okay, as it is a positive V set, it will be beta into V set plus beta V set. Okay, fine. So it will be clamped at plus beta V set and there will be no change in output. Okay, that's why we are calling it stable state. Okay, and what will be the voltage of this point? This point means this VB. As we have considered is ideal diode, so voltage of this point will be the voltage of the diode, that is 0. But in practical scenario, the voltage of this point will be the diode voltage VD, that is will be 0.7 for silicon diode. Okay, so for our convenience, for the time being, we are considering the voltage of this point is 0, and the voltage of this point is plus beta into Vset. Okay, now to change the state from 1 to 0, let us apply a negative going trigger pulse. Okay, at this position we are applying one negative going trigger pulse like this. Negative going, the value of this negative going trigger pulse should be capable enough to make this VID negative. That is the important point. If this point is clamped at some other voltage, in practical scenario I have said it will be 0.7, clamped at 0.7. So the value of this negative going trigger pulse should be enough so that it makes this VID negative. Okay. Now whenever we are applying this negative trigger pulse, the voltage of this one, okay, it should be sufficient enough to make this voltage negative, and negative so that this VID becomes negative. Okay, so the voltage of this point is plus beta into Vset, so definitely this voltage should be greater than this one. Okay, greater than plus beta into Vset. Okay, however, in one sentence we can say the voltage of this input trigger pulse should be enough so that it makes the VID negative. Achha. Now once the VID becomes negative, the output of the op amp becomes 1 to 0, that is plus Vset to minus Vset. It switches from plus Vset to minus Vset. Okay, now I am changing it from beta Vset to minus beta Vset. Okay, see here, whenever the output becomes minus beta Vset, what will be the voltage of this point? That is inverting, non-inverting input terminal. It will become minus beta into Vset. Okay. Achha. And there is another thing. Whenever it becomes a negative voltage minus beta Vset, the diode is no more forward bias. Okay, this negative voltage makes the diode reverse bias. That means it becomes a open circuit. Now it is a negative voltage. This is zero voltage. The point of voltage of this point is zero. So there will be a current flowing in this direction. Okay, from this point to this negative voltage. Okay, which charges start charging this capacitor towards minus Vset. Okay, or you can say that capacitor is starts charging towards minus Vset. The polarity of the capacitor will be minus here and it will be positive. This plate will be positive. Okay, let us consider this voltage is Vc. So the voltage of this point, the input terminal voltage, negative input terminal voltage will be equal to the capacitor voltage. So it is charging negatively. Okay, and this point has been clamped at minus beta into Vset. Okay, now the capacitor is start charging towards minus Vset. Okay, let us say this voltage is minus Vset, minus Vset. Okay, okay, let us move to next slide. Okay, see here we can observe that what is going on, what are the changes are going on with the apply of this one input voltage V in. Okay, that is nothing but our triggering pulse. Okay, negative going triggering pulse. Now as soon as that it receives a negative going triggering pulse, the output switches from beta Vset to minus beta Vset. Okay, sorry, minus Vset, and the capacitor is start discharging or charging negatively towards minus Vset. Now from 0 to minus Vset there will be one point which is equal to minus beta into Vset. Okay, so whenever see here, whenever the voltage of the capacitor becomes minus beta into Vset, the output of the op amp again switches from 0 to 1, that is minus Vset to beta Vset. Why? Because whenever the voltage of the non-inverting terminal becomes less than the inverting terminal, so VID again becomes positive. Let us remember once again. Okay, so when V output of the op amp was switches to minus Vset, okay, minus Vset, this point, this is the most important point of this session. The voltage of this point was minus beta into Vset. Okay, now as soon as the voltage of this point, which is nothing but the voltage of the capacitor Vc, it becomes more negative than minus beta into Vset. Okay, it was minus beta into Vset, minus beta into Vset. Okay, it was clamped at this fixed voltage. Now whenever this voltage of the capacitor becomes more negative than this one, this minus beta Vset, the VID becomes again positive. As soon as the VID becomes positive, the output switches from minus Vset to plus Vset. Okay, which makes the diode D1 again forward biased and it starts conducting. Okay, so this time period T, this is actually the pulse of this generated pulse generated by this monostable multivibrator. Okay, Now we have to calculate what is the value of this t, how we can adjust the value of this t. And okay, and the value of t is depending on actually the value of r and c. Okay, okay, now let us calculate the value of t, that is the pulse width of this monostable multivibrator. Okay, now see, what is t actually? T is nothing but that capacitor taking to charge from 0 to minus beta into V set, isn't it? It was initial voltage was 0, that is the diode voltage. We have considered an ideal diode. So in case of a practical diode, it will be zero point 0.7 volt. However, in this example, it is 0. So it is charging negatively towards minus V set from 0. So 0 is the initial voltage of the capacitor. So it is charging negatively from 0 to minus beta into V set, and that particular time it is taking to charge from 0 to minus beta V set is nothing else but the pulse width of this generated pulse. Okay, now we know this is the basic formula of a charging capacitor. Okay, now to charge or discharge a capacitor, it needs a source voltage, that is we call the final voltage. Okay, that is denoted by Vf. Okay, and the initial voltage is denoted by Vi. Now at any point of t, the voltage of the capacitor, let us consider it is Vct. So Vct can be defined using this equation, that is V final plus V initial minus V final into e to the power minus t by Rc. R and C is the capacitor and resistor of the charging or discharging path. Here this is the R and this is the C, and time is the, this small t is the required time. Okay, now in this example we have know what is V final. V final means due to the voltage it is getting charged or discharged. So the capacitor was negatively charging due to minus beta v, minus V set. Okay, so minus V set is the final voltage in this case. Initial voltage we have considered 0, as it is a ideal diode we have considered. Now at t is equal to capital T is equal to t, Vct, the capacitor voltage was up to minus beta into V set, isn't it? Now we can put these three values in the equation, and we can get minus beta into V set is equal to minus V set plus 0 minus minus V set e to the power minus t by Rc. This capital T is replaced by this small t is replaced by this capital T. Okay, and simplifying this equation we can have t is equal to Rc natural log 1 by 1 minus beta. Okay, now what is beta? We have considered, that is R1 by R1 plus R2. Now if we consider R1 is equal to R2, then this beta becomes beta becomes 0.5. Okay, so it becomes 1 by 0.5, that is 2. Natural log 2 is equal to 0.69. Okay, so value of t is 0.69 Rc. Okay, now the things to be noted is this time period t is depending on nothing but the value of C and R. Okay, that is the feedback resistor R and this capacitor C. So if we change the value of C or R, we can change the value of T. So accordingly, depending on our requirement, we can generate a monostable multivibrator having any pulse width. Okay, that is the end of the session. Thank you.